Okay, cool. So let's start. This is week 2. And first, let's go through a problem. Okay, so this problem is a very kind of classical problem. Imagine we have two spins, spin 1/2, the Hamiltonian. There are like two similar problems in the homework. It's like this. Like this, and ask you to calculate the energy level and also the degeneracy. So because it's a spin 1/2. By the way, whenever you have a Hamiltonian, the first question you should ask yourself is, what's the Hilbert space, right? So in this case, there's no those two spins. Each spin had like a two-dimensional Hilbert space. The total Hilbert space is the tensor product of those two. And this the first one has dimension 2, the second one also has dimension 2, so the total dimension is 4, meaning that if I write this Hamiltonian in some specific basis, then this is a 4x4 matrix. And when we know how to solve 4x4 matrix, and then it means we always have two ways to solve it. First, you can write in some specific basis. For example, in this case, we can write in this up, 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 down, and down, up, and down, down basis. To do that, we know this kind of sigma 1z. So for example, for this term, SD plus S2D, which is like this, D plus sigma 2D. So rigorously, there should be a tensor product identity and also tensor product identity, right? So basically, this operator acting on the first Hilbert space, and this operator identity acting on the second Hilbert space. Similarly, this operator acting on the first Hilbert space, and this second one acting on the second spin. Then you can use this kind of a tensor product to calculate it. So it's like 1100, so minus 1. Tensor product 1100. Similar stuff. This guy is 11001 and 0000, and the minus 1000. And then you get a 4x4 matrix for this element for the first one. And you can do the similar stuff for the second term and also this term. So I won't do it for you because it's just some algebra. You can do it easily by yourself. But if you have difficulties to do it, you can ask me, like, email me, or come to my office hours. We can discuss. Yeah, in this way, we can write down the Hamiltonian as a 4x4 matrix, and then we can solve it. This only applies when the Hilbert space is very small. Here is a 4 dimension, is okay. But if it's like a 8 or like a 16, whatever, then generally we won't do in this way, right? So in that case, we would like to find the complete set of this Hamiltonian and then label the eigencat using the corresponding kind of good quantum number and get the expression for the eigen energy, something like that. So in this case, uh, it's quite straightforward. It's, okay, so naturally we can introduce the oops, operator J as a sum of those two spins. Then J square. The reason why we want to do this is because there's S1 dot S2, right? We know S1 dot S2 can be written in terms of this J square equal to S1 square plus S2 square plus 2 S1 dot S2. And this is nothing. So from this guy, we can solve for S1 dot S2, which is half J square minus S1 square minus S2 square. And S1 square is nothing but 1/2 times 1/2 plus 1 h bar square, right? Which is 3/4 h bar square. So we can replace this operator with this number. Of course, it's a number times identity, but we don't care about the identity, so we just write like this. This is also 3/4 times h bar square. So the reason there are two ways to understand it. First one, because this spin only acting on the first spin, right? The first spin is a spin 1/2, and so this guy acting on any wave function, you would get this number. So we can simply just replace this guy with a number because this operator acting on the Hilbert space like a constant. Another way to understand it is you can write this guy explicitly, which is h bar sigma 1 square, right? This is a definition of S1 for spin 1/2 in the spin 1/2 representation, which is 4 h bar square sigma 1 square. So what's this guy? This guy is sigma 1x dot sigma 1x square plus sigma 1 y square plus sigma 1 z square. So we know this guy is square to unity. So it's 1 plus 1 plus 1, which is 3. So it's 3 h bar square 4. Right? So yeah. So basically we can write the whole Hamiltonian. So into this form, A times this guy is JZ. And plus this guy is like what I said here is this is what's this? It's B times 2J square and minus force like this. So this is our Hamiltonian, and we realize that the complete set is the Hamiltonian JZ and J square. They commute with each other. So we can choose our eigencat to be J and M. In this case, the Hamiltonian, the energy is given by A times M plus B, and this guy becomes 2J plus 1 h bar square minus 3 h bar square divided by 4. And then we know J can be 0 or J can be 1. And you plug in, for this guy, M can be 0, must be 0. This guy, M can be 0 or plus 1 or minus 1. So this is how we solve this kind of problems. And yeah. So the message I want to convey here is Yeah, so when the Hilbert space is small, typically it's a 4-dimension corresponding to 2 spins. We can write down the Hamiltonian explicitly in some basis and then just diagonalize this matrix, right? Another way is kind of manipulate with these terms and write in a nice form, find the complete set and write down the eigencut and then solve it. They are equivalent. So any question about this part? Yeah, they are so they are 2x2 identity matrix because they're only acting on one spin. Yeah, feel free to stop me if you want to ask questions. Sometimes it's easier for me to answer questions and okay, so let's go to the thanks for asking. So let's go to the accidental degeneracy in the hydrogen atom. So the reason why we have this question is because usually if we have as like a rotational invariant system, for example, my potential only depends on the magnitude of the R of this vector R, then it's a kind of a SO3 invariant. In this case, we would expect the energy to be like a dependent on alpha. Alpha is some other quantum number. And also L. L is the quantum number corresponding to this rotational invariance. And in this case, the degeneracy usually is given by 2L plus 1, right? You can say in this example, like what I said here, if I set A to be 0, then the system is given by H Hamiltonian is proportional to J squared, which is rotational invariant. And if A is 0, you can say finally the energy only depends on J, and J can be 0 or 1. The degeneracy is 1 and 3. So it's kind of a 2J plus 1. So this is a typical situation, right? This is what I'm saying here. However, for the hydrogen atom, when your potential is like a 1 over R, of course there's a minus sign, then in this case, it turns out your energy only depends on this other quantum numbers independent of your angular momentum quantum number. And so let's change to this N, the notation we're familiar with. This, but we still, for a fixed N, there are condition for L, which is 0, 1, 2 minus N. So the total for fixed N, the total degeneracy is given by L equal to 0 to N minus 1 to L plus 1 is equal to N squared. So basically, we first, before solving this problem, we would expect N equal to 1, then L equal to 0, the degeneracy is 1, and N equal to 2, there we would expect L equal to 0 and L equal to 1. They should have different energy levels. Has degeneracy 3, and this is 1. But in the real case for the hydrogen atom, it turns out to be N equal to 1, L equal to 0. There's 1 degeneracy. N equal to 2, L equal to 1 and 0. They also degenerate, so it's 4. This is what we call accidental degeneracy, and sometimes also people also call it dynamic degeneracy. So this is a problem. We want to understand why. So actually in the classical mechanics, in the classical situation, we have also kind of a similar thing as you will see. Okay, so imagine I have this kind of potential. This potential is very special because okay, so let's take a general potential which is also SO3 invariant. We know that this what we typically do in the classical physics, classical mechanics. We can write down the equation motion, right, for this dr and also d theta, and this would give us some, d theta dr things like that, according to equation motion. And the point I want to say is, for general potential, the orbital is not closed in general, but the orbital is only closed when the potential is in this form. So imagine I have some, so let's say this is the sun and I have the earth, and there are two special points, like point A and point B. Let's calculate what's the angle after one cycle. So it's 2 times A, B, D theta, right? From A to B corresponding to the half cycle, and times 2 corresponding to the whole cycle. And this is to A, B, and this is nothing but dr, d theta, dr. And for general potential, we know this, you plug in, you do the integral. This guy, generally speaking, is not equal to 2 pi. So, and okay, you can do it by yourself, but okay, so the point is, this guy is 2 pi only if your potential is in this form. So you can see there are already some kind of a like a special for this special thing for this potential. So to understand why this is the case, one also need to introduce. By the way, there's a very famous phenomenon. It's like from the Einstein theory. We know that eventually the potential would get some correction, right? In this case, if it was a precession, there will be a precession like this. I don't know. Yeah.
Very well drawn.
It's not closed in general. What's that?
Should that integral be a pi since it's from A to B?
Yeah. Yeah, there will be some. So to understand the reason, actually quite similar to the quantum case. Of course, first we know there's a conserved quantity, which is the angular momentum, right? And basically it means this guy is a constant. So let's draw this picture and imagine this is there. And so this orbital is perpendicular to this L, right? Because L is the cross product of R and P. It turns out there's another conserved quantity. Let's call it Kearney L. This guy is also conserved. this guy is in this form. Okay, let's assume the potential is let's kr. There's a k factor here, and one can show this as long as we know the Hamiltonian, right? At classical level, we can also show it, and I think this is one of your homework, like in problem set 4. You need to show this, and so let's look at carefully what this guy is. So we know this guy is a constant, it's independent of time. Also, meaning that it's independent of what point you are looking at on the orbital. So this is L, is this guy. And this is M. So this two cross product is R dot P minus P squared R. So okay, let's choose a special point to determine the value of this guy, because we know this current L is independent of odd point, which point we're going to choose, right? So let's choose a special point. Let's choose this point, because at this point, your R is perpendicular to this P. So this term just goes away. So we have something proportional to R. Basically, let's call this point A. This is point O. So this current L is proportional, is parallel to this OA vector, right? Now, if this orbital is not closed, then you would have some, let's say, imagine you have something like this, something like that, and this is the point. This is the O, this is the A. For another circle, you can also choose such a special point such that the R is perpendicular to P. For, let's say, assuming another point is like this point, I don't know. Then from this argument, we can repeat this argument. We get L is also parallel to OB. But we know OA is not parallel to OB, meaning that by contradiction, we know it's impossible. The orbital must be closed to make this argument self-consistent.
Could you explain again what the curl L is?
You mean, okay, so this current L, the expression looks like this. And now we want to really see what this vector looks like. So we write down this L. L is R cross P, and R cross P looks like this, And because we know this L is a constant, meaning that it's independent of the choice of your point. So we choose a special point to determine the value of this current L, right?
Is this just an abstract a quantity that we just define?
Yeah.
And why is it like, why does the curly L over dt is 0? Did you just plug it in?
Okay. That's because you need to write down your Hamiltonian. You need to prove it. Like this, I think it's like a boson bracket, like HL. You need to do it. It's not obvious. And this guy is only true if your potential is kind of a 1 over R.
So we first get the expression of this curly L, then we use that expression to prove that it is not varying in time, right?
Exactly, yeah.
Okay. Thank you.
So if this vector is conserved, is a constant, then the orbital must be closed. This is just another way to say if the potential is 1 over r, then the orbital is closed. Okay, so there's another thing we can remember is the L. This angular momentum is perpendicular to this current L. This is obvious in classical mechanics, classical situation. This L is perpendicular to the plane of the motion, but this current L is along this axis. So they're perpendicular to each other. And this relation holds at the quantum level. And yeah.
I wonder, is the magnitude of L, the curly L, somehow related to the geometry of this orbit? Like the
you can say the magnitude is given by, you can see it right, is k minus p square r plus k r, which is there's one of that. So it's given by the magnitude of this guy. It's not obvious, which k minus p square. Like this, so it's k minus p square r and something like this, right? And this r is the length of this OA, and this p is the momentum at this point A. So what's your question?
I guess my question is that, like, so we're expressing the magnitude of L in terms of the dynamic variables like K, P, and M, but can we just relate it purely to the geometry of the orbit, like the shape of this oval, or?
Well, so we know this is an ellipse, and I guess the equation for this ellipse depends on your definitely depends on your parameter in your Hamiltonian, and that means of course OA you can express in terms of some parameters of this equation, and that's equivalent to say that this OA depends on some parameters in your Hamiltonian, and yeah, definitely related to the geometry of this orbital.
Is it possible that the orbital that is like spirals things and you can't find a point where the r is perpendicular to p?
Spiral, what do you mean by that? You mean like this?
Yeah.
That's kind of exotic. That's an unstable solution, I guess.
So, yeah, but
I mean, this is a dynamic. So what's your point? Like, what's the?
because you say that you claim that we can have a point where at point A where the r is perpendicular to p, and use that assumption to see that there can be a precession. But what if there ain't, like, there isn't any a that is perpendicular, that these two quantities are perpendicular?
So I guess the logic here is okay. So I'm here just provide another way to understand when your potential is 1 over r, the orbital is closed. There, of course, we can make this statement more rigorous. I'm pretty sure you can do that by putting in more math. The another way, the first thing to do it is like what I said here. You can do this kind of integral stuff. here I just provide another way, like by introducing this kernel L to make the connection to the quantum, like we learned in class. Yeah, this is, I guess, it's more like a hand waving argument. Like when I say this kind of a parallel, but you can imagine it makes sense
Yeah.
for most cases, right? Maybe
Yeah,
you can think of some very, very special situations that is kind of suspicious when we apply this kind of pictures. But I'm pretty sure you can verify that is not true by more rigorous math.
sure. Yeah, because after all, we can like just exactly solve this, like
Yeah. Definitely you can solve the exactly.
Sure, thank you.
Is there significance in quantum to the fact that this curly L should be 0 for a circular orbit?
This kernel L is not 0. It's just D kernel L is 0.
No. But for if the orbit's circular, then the point A isn't really uniquely defined. So I would assume that curly L would have to be 0, right? Because you could pick any, like at any point P cross R is 0.
I see.
Or P dot R is 0.
I see.
So then, like, is there significance then in the quantum case to that effect?
That's a good question. I don't know. The short answer is I don't know. Yeah, but that's a good question to ask. Yeah,
I guess in quantum theory, kernel L is an operator, so it doesn't make sense to consider it like at some point or.
Yeah, at the quantum level, we really only care about the algebra. If it's 0, then there's no such. Because eventually at the quantum level, this kernel L will serve the part of the generator of the SO4 Lie algebra, right? If it's 0, then it's nothing interesting.
Yeah. All right, that makes sense. Thank you.
Okay, so let's proceed to see what's happening at quantum level. So at the quantum case, so the Hamiltonian is still the same. So we know there's a special vector at classical level, which is L defined by this guy. Now at quantum level, we can also define a kernel L operator. Let's ignore this hat. To do that, we cannot just write down this because this is not Hermitian. So we can add the Hermitian conjugate and divide by 2. This is the usual trick we do, right? And so this part, the Hermitian is given by.
Did you like, is it R cross P or L cross P?
Oh, sorry, thanks. Yeah, it's L cross P. Oops. And divide by 2. And this guy is Hermitian, so it's like this. And I think that because this is a vector. Okay. Okay. First thing you can prove is this guy commute with the Hamiltonian. So meaning that this according to Heisenberg equation motion, still 0. It's a good. Okay. So another thing is because this L is a vector, basically it transforms like a vector under rotation. So L is a vector, P is a vector, R is a vector. It's not difficult to imagine L is a vector. Kernel L is a vector. Right? So we have this algebra, which is epsilon I the H bar. Okay, so K, right. And another oops, another thing is that you can calculate is this guy equal to, what's this? Okay, so I didn't remember the coefficients, which is I h bar epsilon ij k minus h divided by m. So this h is a Hamiltonian. Yeah, this is true. And combined with this L, the angular momentum, h bar epsilon ij k lk. And okay, so we can kind of rescale. Let's redefine this I or vector as square root of minus m divided by h l. Basically, I'm absorbing this factor into the definition of the kernel L, just to write in a more elegant way. Okay, kernel. Okay, so this definition would not influence the first equation, right? Because the times are the same thing on the right hand side and left hand side together. Okay, there's a tilde, and the second equation becomes like this, and the last one, not the algebra. Yeah. Okay, so there are 6 generators. You can see they form a closed algebra. So there's a this guy. There are 6. Sorry, there are 3 number of them, and this kernel L also 3. So the total is 6, and they form the Lie algebra of SO4. I would say this is not obvious. There are some steps. Of course, you can just look up what's the algebra of the SO4, like then compare with this, and then you realize that this is just the algebra of SO4. But if you don't know that, then it's totally not obvious. There are some steps. Didn't at least yeah, you need to go. Yeah, let's leave that part to next discussion. I will show more steps, but in this case, so you can imagine it's a 6-dimensional vector space. Right, algebra is also a space, vector space, right? There are kind of a six bases, L1, L2, L3, L kernel L1, kernel L2, kernel L3, something like that. So it's just a vector space with some bilinear operation. In this case, it's a commutation. In this case, to further simplify this kind of algebra, we do a rotation. Basically, we redefine the basis of this of this vector space. I just follow the convention. So you can see here's just a rotation by 45 degree, I guess. And there's a factor yeah, for convenience. So under this definition, it's equivalent to redefine your basis in this vector space. And we can write this linear algebra in terms of the new basis. Basically, it's a plus and a minus. Under this new basis, it's decoupled, become become direct sum of two vector space, as you will see. I plus j equal to h1 epsilon ijk and a plus k minus I k minus j minus k. Yeah, we would get this. You can see there's no if you are working within this space, basically the vector space spanned by this a plus 1, a plus 2, a plus 3, you will always stay in this vector space. You won't jump to another space spanned by this a minus 1, a minus 2, a minus 3, minus 1. So they're kind of a separate, and the total the total vector space is just a direct sum. And you realize that this algebra is nothing but the algebra of SU4, SU2, right? SU2. This is why we always write like a SO4 equal to SU2 direct sum SU2. The whole thing is the algebra of the SO4, but we can kind of decouple this basis and decompose it into two. Each one is the algebra of SU2. And in terms of the group, is like this. Of course, without saying anything, it's not obvious why this is true and what this Z2 means. And so in the SO3 case, is we talked about last time. This Z2 means identify this kind of because when the SU2 can be written as the what, like elements A naught times I plus I a vector times sigma, right? This is a general way to square. Basically, the manifold of this guy is a 3 sphere in the 4 dimension. And this Z2 meaning that we identify the minus A naught minus A with A naught A. So here, so you may ask what this Z2 means. This Z2 means imagine this J, okay, let's call this SU4L, L and the R. I just use kind of a notation like this. GL is an element in the first SU2, and the GR is the element in the second one, and you identify this guy. This is what Z2 means in this situation. And one can prove this. Maybe I can do it next time. If I have time today, I can do it. Let's finish the stuff I want to say first. So by the way, any questions so far?
Could you explain what the little g's are one more time?
Oh, little g, just the element in this group.
Okay.
Yeah. Generally, it can be represented using this this way, right? Okay. So then we know this, we can, this SO4, the irreducible representation can be labeled by two numbers. one A plus corresponding to the representation of this first SU2, and the second A minus, this A minus corresponding to the, or yeah, okay, let's call this, okay, let's A, this A. And yeah, and the dimension of this representation, we know that this guy has dimension 2A plus plus 1, right? And this has dimension 2A minus plus 1. It's like a SU2 have a representation of spin 1. Then the dimension of this representation is 2 times 1 plus 1, which is 3. So here, this A plus corresponding to the spin A plus representation of the first spin, and this is spin A minus corresponding to the representation of the second one, and the degeneracy, or the dimension is given by 2 times this number plus 1. And now, because it's tensor product, so the total dimension of this representation is the product of those two numbers. Okay, here's some group theory analysis. Now let's make a connection to what we know. One thing you can verify is L dot kernel L is 0. At classical level, like what I said before, it's very obvious because they're perpendicular to each other. At quantum level, the dot is also 0, but in this case, you need to work out the algebra. But anyway, this guy is 0, meaning that we know this guy relates with A plus and A minus. This guy is also A plus, A minus. Let's write this equation in terms of A plus and A minus. We get A plus square minus A minus square, meaning that A plus square equal to A minus square. So this condition imposes a constraint on our representation. This tells us A plus must equal to A minus. Right? So other representations are unphysical in this situation. This constraint is imposed by physics, right? At a classical level, we have some kind of some pictures and imagine the orbital stuff like that. We get that they are perpendicular. And here, similarly, we can prove they were so perpendicular. If we only look at this kind of a SO4 algebra, the A plus and A minus can be any numbers. They don't need to be equal. But when we look at what is the generator, this A is it's this guy, right? This L is this kernel L is something else. It's not like this. Then it contains some physics, which would introduce this constraint, and it tells us the only physical representation, the only real representation that happens in reality is given by A plus equal to A minus. And then, okay, so we somehow want to connect with the Hamiltonian, right? Okay, so to connect with Hamiltonian, we need to use this equation. This is also obviously true. Remember what I said here. It's just a rotation of matrix, sorry, rotation of the basis, right? It will not change the, this matrix will not change the magnitude, but there's a 1 squared of 2 where will kind of change the length. This is exactly what I said for this matrix. And then you work out what this guy is. And eventually you get something like this. And we know what is L and what is Kearney L, right? They're just they're kind of operators made up of R and P. So you simplify them, you would get, okay, so I also didn't remember the results. I think Yaroslav did this in class, right? Okay, yes. H1 squared plus M2H K squared. I think it's something like this. And okay, we have this. Finally, we connect the generator of our algebra with the Hamiltonian. And in a specific representation, let's say A and A, then the right-hand side, sorry, the left-hand side becomes A plus 1 H bar squared plus the same thing. The right-hand side is this guy. This H becomes the energy. And we can solve for the energy which is given by this. And compare with what we know, we realize that the principal quantum number n equal to 2a plus 1. Remember, A is the representation of the SU2, right? Meaning that A equal to 0, equal to 1/2, equal to 1, equal to like this. Then n equal to 1, 1a equal to 0, and 2 and 3, and so on and so forth. And the degeneracy, remember, is given by this. Degeneracy is the dimension of the representation, right? The representation of this group is given by 2a plus 1 times 2a minus plus 1. In this case, 2a plus 2a minus, they're equal to a. Then it's given by this. And using this identity, we know it's n squared. So by this kind of group analysis, we say that it's the reason why there's a degeneracy is because actually there's a bigger group capture the symmetry of this system. And this is true because the reason is because your Kearney L is a good quantum number. Sorry, is a conserved quantity, and it serves as a generator of the bigger group. And this Kearney L is only conserved when your Hamiltonian is in this specific form. If your Hamiltonian, if your potential is not 1/r, then this Kearney L is not conserved. Then you won't have a generator of Kearney L like this. Then your group is still SO3, and the generator is angular momentum L. Okay, so that's all I want to say today. And any questions? Yeah, I think the time is up. So feel free to go if you have no questions. If you have questions, you can stay here and we can discuss.
You should move the page to the second last page.
Second.
Yeah. Thank you.
Thank you.
Sure.
Wait, so where did you get this h bar square in the second last line?
Where? Oh, okay. So this h bar square comes from the commutation. Okay, so so for example, for L square, it's given by R plus P square. And classically, you would get, okay, so let's look at this. Let's just, this, and this is yeah. Basically, this the H bar square at classical level, there's no H bar because this is nothing but R square P, P square, right? And some equations. But this, if at classical, sorry, at quantum level, we'll do this. If you want to get some like Hamiltonian, basically you want to commute this kind of R and P, and you get some H bar stuff like that. You need to work out the algebra. It's not that difficult because eventually it breaks down to calculate this kind of RP stuff. Right? This L is written in terms of R and P. This current L is also in terms of it's tedious, but it's not difficult.
I see.
Yeah. They're all in terms of R and P. The only commutator you need to know is this.
Okay. Thank you.